Everything we call real is built from things that do not behave like reality at all. Quantum physics began as a solution, but every answer forced scientists into a deeper question, from the mystery of light to the mystery of reality itself. How did the ultraviolet catastrophe turn light into a physics nightmare? How did Planck's constant solve it by forcing energy to come in packets? How did quantized energy explain the colors of atoms? How did the photoelectric effect reveal the true nature of light? What happens during a quantum jump? Why does an electron land like a particle, but behave like a wave? In the double-slit experiment, how do we know what happens when we are not watching? How can superposition make one thing exist in multiple states? How did Schrödinger's equation reveal hidden energy levels? What really is uncertainty? How do electrons have spin, even though they do not spin? Does observation collapse reality, or create infinite worlds? Why is the EPR paradox still one of quantum physics' deepest mysteries? Can quantum tunneling let something pass through a barrier it should never cross? Could consciousness be connected to quantum collapses in the brain? And could quantum tunneling be happening inside your DNA? To answer them, we have to follow the chain of discoveries that turned physics from a science of certainty into a science of possibilities. How did the ultraviolet catastrophe turn light into a physics nightmare? A little more than 100 years ago, physicists were trying to understand why hot objects emit light. At first glance, the question of why molten glass, lava, or an object held over a flame begins to glow seemed very simple. But this small question would become one of the greatest problems in physics at the beginning of the 20th century. Imagine bringing a wooden stick close to a flame. After a while, it begins to glow red, then with a color close to orange. Physicists like Lord Rayleigh knew that the color of this glow was connected to the object's temperature. The sun behaves in a similar way. With a surface temperature of about 5,500 degrees Celsius, it emits light at many different wavelengths, and the combination of these wavelengths appears white to us. Even the human body, at 37 degrees Celsius, does not emit visible light, but it radiates in the infrared region. What Rayleigh really wanted to understand was this: where did this light come from? Could there be a general rule that predicted how much of each color an object at a certain temperature would emit? In other words, could the object's spectrum be explained mathematically? To solve this question, physicists imagined the simplest possible object, an ideal object that absorbed all the light falling on it, but reflected none of it. When you looked at such an object, you would not see light reflected from outside, but only the radiation emitted by the object itself. In physics, this is called a blackbody. The name is actually a little strange, because if a blackbody is hot enough, it does not look black, it glows. But physicists still call it a blackbody. There is no perfect blackbody in the real world, because no object can completely absorb and perfectly emit all light. Even so, stars like the sun come very close to blackbody behavior. But this is where the problematic part began. At that time, atoms and molecules were not understood as well as they are today. Physicists imagined matter as a structure made of tiny particles, vibrating like springs. Rayleigh and James Jeans assumed that these vibrations inside a blackbody were continuously being converted into light. Using classical Newtonian physics and the rules of electromagnetism, they made a calculation. But as the calculation moved toward higher frequencies, it produced a completely meaningless result. The model said that a blackbody should emit an infinite amount of ultraviolet light. This was not a small mismatch. It was a clear collision between theory and reality. Because no object can emit infinite energy, such a thing violates the law of conservation of energy. Experience also shows this. When you put bread in a toaster, the bread is not instantly destroyed by infinite radiation. Hot objects glow, but they do not pour out infinite energy. So the theory was saying one thing, while nature was doing something else. This contradiction was later called the ultraviolet catastrophe, because classical physics seemed to work at low frequencies, but at high frequencies, it began to collapse. Especially in the ultraviolet region, the calculations went to infinity, while nothing like this was observed in the real world. Moments like this are very important in science, because the point where a theory fails is often the place where a new theory is born. Rayleigh and Jeans's calculation was wrong, but it was an extremely productive wrong turn for physics. It made visible the point that classical physics had left incomplete. Around the same time, the German physicist Max Planck was also working on the radiation problem. Planck's goal was somewhat different. He was trying to understand why heat passes from hot objects to cold objects. But while studying this problem, he made a very strange assumption that would solve the dead end faced by Rayleigh genes. According to Planck, a blackbody could not emit light continuously, but only in specific packets. Energy could not take every possible value. It had to come in small pieces, or quanta. The size of these energy pieces depended on the frequency of light multiplied by the number we now call Planck's constant. This idea was not intuitive. It was as if a faucet, instead of letting water flow continuously, could release water only in full glasses each time. But when Planck used this assumption, the calculations suddenly matched real observations. The problem of infinite ultraviolet light disappeared. The ultraviolet catastrophe had been solved. But the interesting part was this. At first, Planck did not fully realize how great a revolution this was. He acted more as if he had solved a mathematical problem. It was as though, when a calculation failed to match the result, he had made a small change and brought the equation into agreement with observation. But this small change would shake the foundations of physics. A few years later, Einstein saw the real meaning of this idea more clearly. If energy was emitted in packets, then light could not be thought of only as a wave. Light also consisted of particle-like packets of energy. Today, we call these packets photons. This idea was later applied to atoms. If atoms emit light, they must do so when their electrons lose energy. But if light is emitted in packets, then electrons must also lose energy not continuously, but in specific steps. In this way, the quantum idea stopped being merely a trick that explained blackbody radiation and began to become the new language of the microscopic world. Planck's small assumption started a great chain that would, over time, turn into quantum mechanics. How does Planck's constant solve ultraviolet catastrophe? Planck's constant sounds like nothing more than a tiny number. But this tiny number is one of the things that determines where the large, smooth world familiar to us ends, and where the strange rules of the quantum world begin. And it really is tiny. Approximately 6.63 times 10 to the minus 34 joule seconds. This number is so small that we do not directly notice its effects in everyday life. Tables remain tables. Stones fall like stones. Cars do not seem to jump forward in packets of energy as they accelerate. The world appears to flow smoothly, but when you descend to sufficiently small scales, this smoothness begins to break down. Reality behaves almost like an image that, when viewed too closely, reveals itself pixel by pixel. Calling it exactly a pixelated reality may not be quite right, but as an idea, it is disturbingly close. Planck did not set out to discover the quantum universe. His aim was much more technical, to find the mathematical form that correctly described the blackbody spectrum. The experimental curve was already known. Nature had shown what it was doing. The problem was that classical physics could not properly explain that curve. Rayleigh Jeans's approach worked up to a point. At low frequencies, it was quite good. But as the frequency increased, the model drifted away from reality. The calculations ran out of control, and the energy climbed toward increasingly absurd values. Something inside classical physics was too free. Energy states were being treated as if they could be divided forever, reduced forever, counted forever. Planck had to stop this infinity. Then, almost in a moment of desperation, as he later described it, he made a strange move. He assumed that particles could not absorb or emit energy in just any amount they wanted. Energy might not be a continuous flow. Perhaps it could only be taken in and given out in certain small packets. In other words, nature might not give change when it comes to energy. A system could not play with energy pieces as small as it wished. A vibration could carry energy only in multiples of a certain basic amount, and that basic amount depended on the frequency of the vibration. The higher the frequency, the larger the smallest energy packet. This is where Planck's constant enters the story. An energy packet is the frequency multiplied by this tiny constant. So what Planck did was not merely add a small number to an equation. That number determined the scale of the smallest steps nature could use in exchanging energy. For classical physics, this was a very strange idea. Classical intuition is built on continuity. It assumes that you can divide something as much as you want, make a value as small as you want, and squeeze infinitely many intermediate values between two energy levels. Planck's move made a small but fatal scratch in that intuition. Energy behaved not like a ramp, but like a staircase. Even stranger, the idea worked. Planck's equation correctly described the blackbody spectrum across all frequencies, not only at low frequencies, but also in visible light and at high frequencies. Where the old calculations exploded, Planck's idea of quantized energy calmed the equation down. The energy distribution that had been racing toward infinity stopped. Nature became calculable again. But Planck himself was not initially very ready to accept that this idea was truly physical. To him, this quantization might have been only a useful mathematical trick, a kind of method for rescuing the calculation. It would even have been more comforting to think that Planck's constant would eventually go to zero, because if the constant was zero, the gaps between energy levels would disappear as well. The quantum idea would vanish, and classical continuity would return. But the constant did not turn out to be zero, and it did not disappear from the equation. On the contrary, it became increasingly central in the history of physics. Planck's constant did not remain limited to blackbody radiation. It appeared in Heisenberg's uncertainty principle. It appeared in the de Broglie wavelength. It appeared in Schrödinger's equation. It appeared in the energy levels of atoms. It appeared in the energy of photons. It was as if the same tiny signature stood at every doorway of the microscopic universe. And then Einstein arrived. Planck had quantized the energy of vibrating particles. Einstein took a more radical step. Perhaps the thing being quantized was not only matter, perhaps light itself was also made of packets. This idea was much stranger, because light already behaved like a wave. It interfered, it diffracted, it spread. There was strong evidence that it was a wave. But Einstein took Planck's idea seriously and said that light also behaved as particle-like packets of energy. Today, we call these packets photons. The energy of each photon is equal to its frequency multiplied by Planck's constant. Red light has a lower frequency, so its photons carry less energy. Ultraviolet light has a higher frequency, so its photons carry more energy. So what we call color is not merely a property perceived by our eyes. Color is also related to the size of energy packets. This idea changed atoms as well. If light is absorbed and emitted in packets, then the electrons inside atoms must also be unable to change their energy continuously. Electrons had to move between specific energy levels. When they dropped from one level to another, they emitted a photon. When they climbed upward, they absorbed a photon. The inside of the atom was not a simple machine in which tiny planets moved in smooth orbits. It was more like a strange energy staircase, where only certain steps were allowed. And the scale of that staircase was determined by Planck's constant. That is why what Planck did was not merely correct the blackbody spectrum. He left physics with a much deeper question. What if nature, at its most fundamental level, is not continuous? What if there is not always a smaller step in between? What if the fabric of reality is not smooth in the way we imagine, but built out of quantum packets? Planck may not have intended to begin this revolution. Perhaps he was only searching for the right equation. Perhaps he first saw his assumption as a temporary trick. But science sometimes advances in exactly this way. A small mark you place in order to solve a problem becomes a doorway into the deepest structure of nature. Today, Planck's constant is not just a tiny number sitting inside a formula. It appears in the color of the sun, in the spectra of stars, in lasers, LEDs, computer chips, and almost every equation of quantum mechanics. Planck was trying to explain the blackbody curve. What he found was the first great clue that the universe is not smooth. How does energy quantization explain the colors of atoms? Thinking of energy as behaving like a continuous flow feels very natural, because the world we see in everyday life tells us exactly that. The brightness of a lamp can increase gradually. A car can raise its speed step by step. A stove can become hotter and hotter. Everything appears to change through infinitely small intervals. From this point of view, Energy also seems like a smooth quantity that can take any value we want. But when we descend into the world of atoms, this intuition begins to break down. At the smallest scales, nature does not always distribute energy like a continuous flow. Sometimes, energy can only be absorbed or released in specific packets. This idea is called energy quantization, or the quantization of energy. At first glance, this idea seems strange, because it raises a question. Why should a system not be able to have any amount of energy at once? Why should the values in between be forbidden? Why should an electron not exist around the nucleus with any possible energy, but only at certain energy levels? One of the most striking answers of quantum mechanics appears here. At the atomic scale, energy is often like the steps of a staircase. A particle can be on one step, it can jump to another step, but it cannot remain stably between two steps. In the everyday world, we imagine motion as if we were walking along a ramp. In the quantum world, however, many things work according to the logic of a staircase. One of the most important consequences of this idea appears in atoms. Electrons in an atom do not move around the nucleus with random energies. Each electron can exist only at certain energy levels. If an electron is at a low energy level and absorbs energy from outside, it can move to a higher level. But the amount of energy required for this transition must be matched exactly. Less is not enough. More does not produce the same transition either. The electron absorbs exactly the specific difference allowed by nature and jumps to a higher level. The same thing happens in the opposite direction. When an electron drops from a higher energy level to a lower one, it releases the energy difference as light. This light does not have a random energy. Its energy is determined by the difference between the two levels. That is why atoms do not emit light in every color. Each element has its own unique light signature. The spectral lines of hydrogen, helium, sodium, or neon are different because each one has different electron energy levels. This is a very deep idea. The identity of an element can be read not only through its atomic number, but also through its allowed energy steps. This is why we can analyze the light coming from a distant star and understand which elements it contains. The missing or glowing lines in the star's light show which energies atoms have absorbed or emitted. Energy quantization is not limited to atoms alone. The vibrations of molecules, their rotational motion, the behavior of electrons in solids, the working principle of lasers, semiconductors, LED lights, quantum computers, and even a large part of modern electronic technology all rely on this idea. If energy were completely continuous at every scale, the atomic structure, chemistry, light emission, and electronic circuits we know today would be very different. The truly surprising point is this. Quantization shows that, at small scales, nature is not random, but extremely selective. A system cannot do everything. It can only move between allowed states. Energy is absorbed or released according to the differences between those states. That is why, in the quantum world, the question, how much energy, often turns into the question, between which two levels? In everyday life, we do not notice this discontinuity, because in macroscopic objects, energy levels are extremely close to one another. The gaps between them are so tiny that they appear continuous to us. Just as a staircase can look like a straight line when seen from far away, but when we look closely enough, we see that nature does not present us with a smooth surface, but with a stepped structure. This is why energy quantization is one of the fundamental gateways into quantum mechanics. It tells us this: the deepest structure of the universe is not as fluid as our classical intuitions imagine. At the atomic scale, energy does not behave like a silent rain, but like individual falling drops. Each drop has a specific size. Each transition demands a specific price, and the entire visible order of matter is built upon these invisible steps of energy. How did the photoelectric effect reveal the true nature of light? The photoelectric effect is one of those ideas that sounds simple at first. It involves light, electrons, and a piece of metal. But the reason it matters is much bigger than that. It is one of the clearest pieces of evidence that light does not always behave like one smooth wave spreading through space. In some situations, light acts as if it arrives in separate little packets of energy. We call those packets photons. Now, This might feel strange, because we already know that light behaves like a wave. It can diffract, it can interfere, it can spread out in patterns, just like ripples on water. For a long time, that seemed like enough. Light was treated mainly as a wave. But then physicists looked at what happens when light shines on a metal surface, and the wave picture alone began to fail. Imagine a metal plate. Inside that metal, there are positive ions and electrons that can move around freely. If you shine light onto the metal, sometimes electrons are knocked off the surface. These emitted electrons are called photoelectrons. If light were only a wave, we might expect something very simple. A brighter light should carry more energy. So even if the light had a low frequency, making it brighter should eventually give the electrons enough energy to escape. The electrons could slowly collect energy from the incoming light until they had enough to jump off the metal. But that is not what happens. If the frequency of the light is too low, no electrons are emitted. No matter how bright the light is, you can increase the intensity. You can shine the light for longer. Still, nothing happens. But once the frequency rises above a certain value, electrons suddenly begin to leave the surface. That value is called the threshold frequency. This tells us something very important. The key is not just how much light there is. The key is how much energy each individual photon carries. The energy of a photon is given by the equation E equals hf. Here, f is the frequency of the light, and h is Planck's constant. So a higher frequency means a more energetic photon. If one photon does not have enough energy to free an electron from the metal, then the electron will not escape. Sending more low-energy photons does not solve the problem. In the ordinary photoelectric effect, one electron absorbs one photon. It does not collect energy from several photons and then decide it has enough. This also explains why intensity works differently from frequency. Increasing the intensity means increasing the number of photons. If those photons already have enough energy, more photons can knock out more electrons. But they do not make each electron fly away with more maximum kinetic energy. The maximum kinetic energy depends on frequency. To measure that kinetic energy, physicists use an evacuated tube. The air is removed so that electrons can travel from one plate to another without crashing into gas particles. Light shines on one plate. Electrons are emitted and moved toward the other plate, producing a current. Then a battery is connected in a way that tries to stop the electrons from reaching the other side. The voltage is increased until the current becomes zero. This voltage is called the stopping potential. The stopping potential tells us the maximum kinetic energy of the emitted electrons. If the voltage is just strong enough to stop them, then the electrical energy used to stop them matches the kinetic energy they had after leaving the metal. Now, change the frequency of the light. At low frequency, nothing happens. No electrons come out. Then, at the threshold frequency, emission begins. Above that point, as the frequency increases, the maximum kinetic energy of the electrons also increases. This is where the work function comes in. The work function is the minimum energy needed to remove an electron from a particular metal. Different metals have different work functions. The photon first spends energy freeing the electron. Whatever energy is left becomes the electron's kinetic energy. So the photoelectric equation is really just energy accounting. The energy left over equals the energy given by the photon minus the energy needed to free the electron. If the photon energy is too small, no electron is emitted. If it is just enough, the electron escapes with no extra kinetic energy. If it is greater than the work function, the electron leaves with speed. And this is why the photoelectric effect was so important. It showed that light is not just one big, smooth wave of energy. It comes in specific, individual packets. Each photon carries an amount of energy determined by its frequency. One photon interacts with one electron, and if that photon is not energetic enough, brightness alone cannot make the electron escape. In other words, the photoelectric effect showed that light is quantized. It arrives not as a continuous flow, but as tiny pieces of energy. That single idea helped open the door to quantum physics. What happens during a quantum jump? Since the very beginning of quantum mechanics, there has been a great debate over how its strange predictions should be interpreted. And at the very center of this debate is the idea we call the quantum jump, or quantum leap. That is, the sudden transition of a quantum system from one state to another, almost as if by miracle. For a long time, these transitions seemed unobservable, unpredictable, and almost like tiny ruptures hidden inside nature, at least until recently. The idea of the quantum jump is one of the founding concepts of quantum mechanics. In fact, it is almost like the first great symbol of quantum weirdness. Today, even in everyday language, the phrase quantum leap is used, but often in a way quite far from its original meaning. The real idea is this: electrons in atoms jump randomly and instantly from one orbit, or energy level, to another, without ever occupying the space in between, as if the electron disappears in one place and reappears somewhere else. This idea has become so deeply embedded in the way we imagine atoms that most people do not even think to question it. But one of the most important founders of quantum mechanics never truly believed in it. Erwin Schrödinger never accepted the idea of quantum jumps. But in his time, the measurement precision needed to disprove it did not exist. The experimental tools required for that were not available in Schrödinger's era. Now they are. And the reality of the quantum jump has finally been tested directly. It all began in 1913. The great Danish physicist Niels Bohr was trying to explain emission spectra, the sharp-colored lines that appear when a simple gas tube is excited with energy. Bohr was inspired by Max Planck's recent success. Planck had explained the colors of light emitted by a heated object, the blackbody spectrum, by assuming that light consisted of indivisible packets of energy. Bohr applied a similar restriction to atoms. He said that the energy levels of electrons were quantized, meaning that they could possess only very specific energies depending on the element. Electrons would then jump between these energy levels by emitting or absorbing a photon corresponding to the energy difference between them. The result was the Bohr model of the atom. It was one of the first serious attempts at quantum theory, and it explained the specific frequencies of light observed in hydrogen's emission spectrum quite neatly. It failed for more complex elements, but it had still opened a great door. Bohr's work inspired Werner Heisenberg and Erwin Schrödinger in 1925 to develop the first complete formulations of quantum mechanics. This new theory would eventually explain the spectra of elements of every level of complexity, and much more besides. But one thing was still mysterious. What was actually happening during a quantum jump, and what determined when a quantum jump would occur? To answer such questions, Bohr and Heisenberg developed the Copenhagen interpretation. According to the Copenhagen interpretation, transitions between quantum states are fundamentally random. The dice are thrown, and the system suddenly moves into another state. An electron goes from one energy level to another, without moving through the space in between. Copenhagen says that measurement collapses the wave function. Today, this is often understood as interaction with the environment causing a state transition, meaning a quantum jump. But one person was not impressed by this idea at all. Erwin Schrödinger, the inventor of the wave function. When he visited Bohr's home in 1926, he famously said something to the effect of, "If we still have to put up with these damned quantum jumps, then I wish I had never had anything to do with quantum theory." During this visit, Schrödinger became ill and had to stay in bed. Perhaps he really was that disturbed by the idea, but even that did not help. According to the story, Bohr continued trying to convince the sick man of the Copenhagen worldview. Bohr's efforts did not succeed. In 1952, Schrödinger published a two-part paper titled, "Are There Quantum Jumps?" In it, he compared the theory of quantum jumps to the epicycles in the old Earth-centered theory of planetary motion. To him, both epicycles and quantum jumps were clever constructions of the human mind, but they were not true descriptions of nature. So why did Schrödinger hate quantum jumps so much? Put simply, they did not seem natural or physical to him. They looked like a patch added to cover up a phenomenon that quantum theory had not yet properly explained. This debate was actually only one part of the larger fight over the quantum nature of reality. On one side was the Copenhagen interpretation. On the other side was, roughly speaking, everything that was not Copenhagen. The most famous sentence from this second side came from Einstein. God does not play dice with the universe. This was a reaction against the idea at the heart of Copenhagen, that subatomic events are fundamentally random or probabilistic. Schrödinger had his own objections as well. For him, everything was based on waves, and these waves were not completely different from other classical waves. He thought that many spooky quantum phenomena could be explained through classical resonance effects. He rejected the idea that the photon was an indivisible packet of energy, and he was even skeptical of the idea that electrons jumped between discrete energy levels. According to him, the same emission spectra could also be obtained by thinking of these levels as fundamental modes of vibration on a drumhead or a guitar string. The atomic electron could be seen as a superposition of multiple vibrational modes. This would mean that, instead of making an instantaneous jump during each transition, the electron could move smoothly through intermediate states. According to Schrödinger, much of the problem came from Bohr and others using the behavior of systems made of many particles to draw conclusions about the behavior of individual particles. He thought that even talking about a single particle was meaningless. In his view, we were never really performing experiments on only one electron or one atom. In thought experiments, we sometimes assumed that we were, but that inevitably produced strange conclusions. That was how things stood in 1952. Because at that time, we had never seen a single photon emitted from a single quantum jump in a single atom. But over time, we learned how to do it. By the 1980s, physicists had managed to trap and cool a single atom with lasers. Then, in 1986, 3 different teams, almost simultaneously, observed quantum jumps in such an atom. The logic of the experiment was this: a single atom, such as mercury or barium, was exposed to a laser beam tuned exactly to the energy difference between 2 electron levels. If the electron was in the first level, it should absorb a photon from the laser and rise to the second level. Then, if it fell back to the first level, it should emit the same kind of photon in a random direction. When the right energy levels are chosen, this process happens very quickly. The electron becomes almost locked between the 2 levels. In the 1986 experiments, the electron in the trapped atom was moving back and forth between the levels about 100 million times per second. The individual photons emitted during this process could not be seen directly. Instead, the single atom simply glowed, meaning it fluoresced. But to see an individual quantum jump more directly, one more energy level was needed. Let us call this the third level. The third level is much more stable than the second level. When the electron moves there, it can take seconds to fall back down. While the atom is happily glowing under the first laser, a second laser moves the electron from the first level to the third level. Suddenly, the atom goes dark. The fluorescence stops, because the electron is trapped in the third level and can no longer move between the first and second levels. After a while, the electron decays and the glow begins again. In this way, physicists obtained fairly direct evidence for a single quantum jump, and the timing of the falls from the third level appeared completely random, exactly as Bohr had predicted. So was the matter settled? Was Schrödinger wrong and Bohr right? Not so fast. The jump appeared random, but was it truly instantaneous? Or was the electron passing through intermediate states during the jump? There was no way to say. Not until more than 30 years later, when technology reached the point where individual quantum jumps could not only be seen, but followed throughout the process and even stopped halfway through. This time, instead of a real atom, physicists used a kind of artificial atom made from 2 superconducting circuits. The 3 energy levels of this artificial atom corresponded to the number of quanta of electromagnetic energy stored in the circuits. Researchers placed these artificial atoms inside a microwave cavity. This allowed the atom to transition between states, in a way similar to what a laser does, but it also allowed the state of the system to be monitored with much higher resolution than in the 1986 experiment. This allowed researchers to look closely at the quantum jump, and finally, they could test whether it was truly instantaneous. The result was this: no, it was not instantaneous. The jump was a continuous transition lasting a few microseconds, moving through intermediate states. Moreover, This transition was extremely well explained by theory, especially by quantum trajectory theory. But what about randomness? The intervals between jumps seemed random, just as Bohr had thought. But immediately before each jump, the system began to change, allowing the researchers to predict the approaching jump. This ability to predict it even allowed them to reverse the quantum jump in mid-flight by adjusting the microwave field. At this point, one cannot help wondering, if the beginning of a quantum jump can be predicted, and if the path it follows is very well explained by theoretical calculations, does the whole process really arise from fundamental randomness? Or is there a deeper, deterministic mechanism underneath? Schrödinger and Einstein would probably have liked that question. For now, the picture stands in a strange balance. Both Bohr's side and Schrödinger's side seem to have gained new evidence. For a long time, physicists avoided asking which interpretation of quantum mechanics was correct. To many, it seemed like a matter of philosophical preference. Either you would roll dice with Bohr and Heisenberg in Copenhagen, or you would ride Schrödinger's continuous and deterministic wave. But experimentalists are finding more clever ways than the skeptics imagined. Almost a century after the debate between Bohr and Schrödinger, we may be standing on the edge of the next quantum jump. The edge of learning whether quantum jumps are truly instantaneous or continuous, and perhaps even whether the quantum world is built on fundamentally random processes or governed by the rigid, deterministic mechanics of space-time. Why does an electron land like a particle, but behave like a wave? One of the most surprising facts in physics is this: everything in the universe, from light to electrons, from atoms to the smallest structures that make up matter, can behave both like a particle and like a wave at the same time. All the strange ideas we hear about quantum physics, Schrödinger's cat, God playing dice, spooky action at a distance, actually revolve around this basic idea. Because much of the weirdness of the quantum world comes from the fact that everything has both a particle nature and a wave nature. At first glance, this can seem completely irrational. In the everyday world, waves and particles are very different from each other. We see a wave spreading across water. A stone in our hand, however, is a solid object located in a definite place. One spreads, disperses, and overlaps. The other has a definite position, boundary, and weight. So why were physicists forced to combine these two different things inside the same concept? In fact, physicists did not do this suddenly or arbitrarily. No one simply sat down and decided, let light be both a wave and a particle. What led them to this idea was evidence that accumulated slowly. Like pieces of a puzzle, clues from different experiments came together, and eventually, the dual nature of the universe appeared. One of the first major figures to bring this dual nature of light seriously into discussion was Albert Einstein. But Einstein was not starting completely from zero. He was taking an idea that Max Planck had proposed earlier and pushing it much further. Planck had tried to explain why hot objects emit light in certain colors. For example, the glowing filament of a light bulb. To explain this, he had to make a very strange assumption. Energy was not emitted like a continuous flow, but in small and discrete packets. The size of these packets depended on the frequency of light. At first, Planck was not very pleased with this idea. He saw it more as a mathematical solution, but Einstein took the physical meaning of this idea seriously. If energy was emitted in packets, then light itself could not be merely a smooth wave. Light had to consist of particle-like packets carrying specific amounts of energy. Today, we call these packets photons. This idea explained how light could knock electrons out of metal surfaces. In other words, it explained the photoelectric effect. Even though those who believed light was only a wave did not like this idea, the results worked so well that it became impossible to reject it completely. Then, another piece of the puzzle came from Ernest Rutherford. When Rutherford's students sent alpha particles toward gold atoms, they saw that most of them passed through almost without deflection, but some unexpectedly bounced back. This was astonishing. Because this result showed that most of the atom's mass was concentrated in a very small region, the nucleus. The picture of the atom we see in schools today, where electrons orbit the nucleus like tiny planets, largely comes from Rutherford's model. But this model had a major problem. According to classical physics, it could not work. Because classical physics tells us this: a charged particle moving in a circular path should emit energy. If electrons were orbiting the nucleus, they should continuously emit light, lose energy, and fall into the nucleus in a very short time. In other words, Rutherford's atom should have collapsed into itself almost as soon as it existed. But atoms exist. Matter exists. We exist. So Niels Bohr took a very radical step. Perhaps the rules of classical physics did not apply inside atoms in exactly the same way. According to Bohr, electrons could exist only in certain special orbits. And while they were in those orbits, they did not emit light. Light was emitted or absorbed only when an electron moved from one orbit to another. Moreover, the frequency of the emitted light depended on the energy difference between these two levels. This model solved Rutherford's problem. It also explained why atoms emit light only in certain colors. Each element had its own unique energy levels. That is why each element carried its own distinctive light signature. But there was still an important missing piece in Bohr's model. Why were these special orbits special? Why did nature allow only certain orbits? This is where Louis de Broglie entered the story. De Broglie proposed a very simple but shocking idea. If light, which everyone knew as a wave, could behave like a particle, then perhaps the electron, which everyone knew as a particle, could also behave like a wave. This idea made Bohr's special orbits meaningful. If the electron was a wave, then around the nucleus it could form only wave patterns that matched up properly with themselves. Just as a guitar string can support only certain vibrations, an electron inside an atom can exist only in certain wave states. In this way, the special orbits stop being arbitrary. They become the natural result of the electron's wave nature. After this idea was proposed, scientists began testing whether electrons really behaved like waves. And before long, wave behavior was observed in electrons. Today, we see this most clearly in the double-slit experiment. You send individual electrons toward a barrier with two slits in it. Each electron hits the screen at a definite point. In this sense, it behaves like a particle. But when you repeat the experiment many times, the individual points on the screen do not form a random stain. Instead, a striped interference pattern, characteristic of waves, appears. So individual electrons arriving one by one seem to behave like particles, but the pattern produced by many electrons shows that they behave like waves. This is the mystery at the center of quantum mechanics. Particles behave like waves, and waves behave like particles. This is not just a minor detail. The entire strangeness of the quantum world grows out of this. The measurement problem, uncertainty, superposition, probability, and all the other strange consequences of quantum physics arise from this basic duality. Light is not only a wave. The electron is not only a particle. The world inside atoms behaves neither completely like stones, nor completely like water waves. It obeys a deeper rule between the two, foreign to our intuitions but confirmed again and again by experiment. And the rest of quantum mechanics falls into place around this first strange idea, like a puzzle. In the double-slit experiment, how do we know what happens when we are not watching? If we want to understand the mystery at the heart of quantum mechanics, we need to begin with the double-slit experiment. Richard Feynman saw this experiment as the fundamental secret at the heart of quantum mechanics. Because there are many strange things in the quantum world, but the double-slit experiment gathers all of that strangeness into a single scene. In a way, it shows you what quantum mechanics is about through one experiment. First, let us imagine a simple situation. We have a light source. This light is sent toward a screen with two thin slits in it. Let us assume that the light is monochromatic, meaning that it has a specific wavelength. A normal light bulb gives off white light, and that light consists of many colors and many different wavelengths. But here, let us imagine that we are using light with only one wavelength. Light travels in waves, just like the rings formed when a stone falls into a pond. When the light reaches the two slits, it squeezes through them. Then each slit behaves almost like a new light source on the other side of the screen. The light spreads out, diffracts, and the waves emerging from the two slits overlap with each other. This is where interference appears. When the crest of one wave meets the trough of another wave, they cancel each other out. When one crest meets another crest, they reinforce each other. As a result, a pattern of bright and dark lines appears on the screen behind. This is called an interference pattern. In some regions, the waves have destroyed each other. In other regions, they have combined in the same phase and strengthened each other. Up to this point, everything is normal. This is not yet the real strangeness of quantum mechanics. The fact that light behaves like a wave has been known since the early 19th century. Now imagine doing the same experiment not with waves, but with particles. For example, with grains of sand. This time, we do not have waves spreading out, hitting the two slits and passing through both of them at once. We have small particles moving one by one. Each grain of sand goes either through one slit or through the other. As a result, two regions form on the surface behind, one behind the first slit and the other behind the second slit. In other words, we see two peaks. This is particle behavior. While the bright and dark lines we see with light show wave behavior, the two separate accumulation regions we see with grains of sand show particle behavior. So what happens if we do the same experiment with atoms? Imagine that we have a source of atoms. This source sends atoms toward a screen with two slits. Because atoms are very small, we cannot see them directly. So we place a sensitive screen behind. When an atom hits this screen, a small point of light appears. This allows us to understand where the atom has arrived. First, let us close one of the two slits. In this case, nothing strange happens. Most of the atoms are blocked by the first screen. The ones that pass through the open slit reach the screen behind. On the screen, we see points of light around a single region. Some atoms may have hit the edge of the slit and been deflected a little, so a small spread appears. But this is not hard to understand. The atoms seem to behave like small particles. The first real mystery begins when we open the second slit. Because when the second slit is opened, instead of seeing two separate bands of atoms on the screen behind, a pattern appears that resembles the interference pattern we saw with light. It is as if the atoms have passed through the slits, not like particles, but like waves. It is as if probability waves emerging from the two slits have mixed with each other, reinforcing one another in some places and cancelling each other out in others. At first glance, you might try to give this an ordinary explanation. Maybe the atoms are interacting with one another. Maybe one group of atoms decides to go to one region, while the others scatter toward another region. Maybe there are some forces between them that we do not know about, and these forces cause them to form such a pattern on the screen. That would be strange, but it would still not be extremely mysterious. After all, we could say that we do not know how atoms behave with one another, but we can make the experiment sharper. Let us send the atoms not all at once, but one by one. Let us send one atom and wait for it to pass through the slits and reach the screen. Then send the second atom, then the third. In this way, we do not allow two atoms to interact with each other at the same time. At first, random points appear on the screen. Each atom arrives as a small dot, like a particle. It appears in one place. It does not arrive as a faint cloud spread across the screen. It does not look like a dispersed wave, but like a tiny object striking a definite point. But when you continue the experiment for a long time, the same interference pattern slowly appears. This is where the problem lies. Each atom has been sent alone. It has not spoken to other atoms. It has not moved together with other atoms. Yet each one has formed a small part of the larger wave-like pattern. A single atom has behaved as if it somehow knew that both slits were there. So how does it do this? An atom is a very small local particle. You send it toward a screen with two slits. After a while, a single point of light appears on the screen behind. The atom appears in a definite place. And yet, its behavior is not as if only one slit exists. It seems to have been affected by the existence of both slits. Then the question arises, how does a single atom know about both slits? Does it split in two? Does it pass through both slits at once like a cloud? Or is what we call a particle something far stranger than we think? To understand this, we can be even more cunning. Let us try to watch which slit the atom passes through. Put a detector next to the upper slit. If the atom passes through the upper slit, Let the detector beep or flash. If it does not, let us assume that the atom passed through the lower slit. When you perform the experiment in this way, the atoms really do seem to pass through either one slit or the other. Sometimes the detector indicates the upper slit, sometimes it does not. On the screen, the points also form in a way that matches which slit the atoms passed through. But the result is no longer the same as before. The interference pattern disappears. The moment you observe the atoms, the wave-like behavior vanishes. The system begins to behave like a particle. It is as if the atom, the moment it is watched, stops being a blurry probability passing through both slits and turns into a definite particle traveling along a single path. We can play one final trick. Let us leave the detector there, but quietly unplug it. Let us make it look as if we are watching the atoms, but actually make no measurement. Let the detector remain in place, but not work. When you perform the experiment again, the interference pattern returns. So the issue is not the detector physically being there. The issue is whether information is actually obtained. If you can learn which slit the atom passed through, the interference disappears. If you do not obtain that information, the interference returns. This is why the double-slit experiment is so unsettling. Atoms arrive at the screen like particles, but along the way, they behave like waves. When you try to learn which path they took, this wave-like behavior disappears. When you do not measure them, even atoms sent one by one eventually form a wave interference pattern. If you can explain this using only common sense and classical logic, you truly deserve a great prize. Because the mystery at the center of quantum mechanics stands exactly here. When we are not looking, nature behaves like possibilities. When we look, it gives one definite real result. So how do we know what happens when we are not looking? Not by secretly watching the particle's path. That would already change the experiment. We know it from the final pattern on the screen. When no which path information is collected, the interference pattern appears. When that information is collected, the pattern disappears. In other words, the particle's journey remains unseen, but the result it leaves behind tells us that the unobserved case was different. The screen becomes the evidence. How can superposition make one thing exist in multiple states? Here is a riddle. Musicians and music lovers know that different instruments can play the same note. But if the note is the same, why do they sound different? If you understand the reason, you also understand one of the most important principles of quantum physics: superposition. Let's break it down. Sound is produced by vibrations that can come from many different sources. These vibrations cause air pressure to rise and fall, and that is what our ears detect. The speed of a vibration is called frequency, and it is measured in hertz, meaning the number of repetitions per second. A musical note has a specific frequency. For example, the note A near the middle of the piano sounds like this. Another instrument, say a guitar, can play the same note. So why do they sound different? Imagine a string fixed at both ends, such as a piano string or a guitar string. This string has many possible ways of vibrating. There may be a single peak in the middle between the two ends, or there may be two peaks, or three, and so on. Each of these different forms of vibration happens at a different frequency, which is why we hear them differently. If the string vibrated in only one single mode, then in principle we should hear only that frequency, but that is not what actually happens. When a piano string is struck, or when a guitar string is plucked, the total vibration is much more complex. Each mode of vibration contributes a certain amount to the total vibration, and exactly how much each one contributes determines the unique sound of the instrument. So the total sound is a combination of all possible frequencies layered on top of one another. This is where the connection to quantum physics appears. A quantum system has many possible frequencies. Physicists call these basis states. The total state of the system is a combination of each of these possible basis states. This combination is called superposition. A quantum bit, or qubit, is one of the simplest quantum systems, and it usually has two basis states called 0 and 1. Just as the total vibration of a musical instrument is a combination of different frequencies, the total state of a qubit is a combination of 0 and 1. Although this wave-based analogy is powerful, there are some important differences between quantum superposition and the superposition of waves. These include how they are measured and how quantum superposition is physically interpreted. The details are somewhat complicated. But just as the superposition of waves in music leads to richer and more interesting sounds, quantum superposition leads to richer and more interesting technologies. From running faster algorithms in quantum computers to securing communication through new methods of cryptography. And it all begins with vibrating strings. You could say the idea has a nice ring to it. How did Schrödinger's equation reveal hidden energy levels? You can think of a particle's motion in two different ways. Either you imagine it as a small object following a definite path, or you imagine it as a wave spreading through space. In classical physics, when a particle travels from point A to point B, we can imagine infinitely many possible paths. But the real motion selects one special path from among all these possibilities. And the idea that determines this path is based on one of the oldest and most powerful principles in physics, the principle of least action. Roughly speaking, this idea says the following: when a motion takes place, nature chooses, among the possible paths, the one that is in a certain sense the most economical. Here, action does not mean action in the everyday sense. It is an abstract quantity connected to an object's mass, speed, path, and energy. At first, it may seem strange, but for physicists, it is a very deep guide. Because to find the real path of an object, you consider all possible paths, and then choose the one that makes the action most suitable. This idea gradually became a more powerful mathematical language through figures such as Maupertuis, Euler, Lagrange, and Hamilton. Lagrange translated Newton's world, full of forces and vectors, into a purer language of energy. He showed that the same physical results could be reached by using an object's kinetic energy and potential energy. Hamilton then gave this idea an even deeper direction. According to him, there was a surprising similarity between mechanics and optics. We can describe light in two different ways. On the one hand, we describe it through wave fronts. All the points reached by light at a certain moment form a wave front. On the other hand, we describe light as rays, that is, as lines following certain paths. These two descriptions are not independent of each other. If you know the wavefronts, you can determine the direction of the rays. If you know the rays, you can find the wavefronts. Hamilton's great intuition was this: the same thing might also be true for particles. The classical trajectory of a particle resembles the rays of light. But what is the wavefront of this motion? According to Hamilton, its counterpart is action. In other words, we can also think of the motion of a particle through surfaces of constant action. In this way, even in classical mechanics, a hidden duality appears between the path of a particle and a wave-like structure. This was exactly Schrödinger's starting point. In his famous papers published in 1926, he took Hamilton's analogy between optics and mechanics very seriously. Because in optics, one thing was already known: light could be explained more fundamentally as a wave, while rays were only an approximate description that appeared in a certain limit. When the wavelength was very small, the ray picture worked. But when the wavelength became important, the ray picture broke down, and the real explanation was left to the wave equation. Schrödinger asked this: what if the same thing was happening in mechanics? What if particle trajectories were also only an approximate picture, valid in a certain limit? What if the strange quantum conditions inside atoms were actually the natural result of a more fundamental wave equation? At that time, physicists were introducing certain rules to explain the energy levels of atoms. Energy and angular momentum could take only specific values, but these rules looked somewhat artificial. They seemed like restrictions added to nature afterward. What Schrödinger wanted to do was not to assume these quantum conditions, but to make them emerge naturally from a deeper principle. For this, he started from the Hamilton-Jacobi equation. This equation described classical particle motion through action. Schrödinger made a change of variables that would transform this structure into a new wave function. Then he turned the classical problem of motion into a new variational problem. This was the real leap. The aim was no longer to find a single path for the particle, but to determine a wave function spread through space. From this approach emerged the fundamental equation we now call the time-independent Schrödinger equation. When the equation was applied to the hydrogen atom, something remarkable happened. The energy levels came out discrete by themselves. It was no longer necessary to impose these levels from the outside. They were the natural result of the equation. Just as a vibrating string can vibrate only at certain frequencies, the electron in an atom could exist only in certain states. That is why what Schrödinger did was not merely write a new equation. He placed wave logic inside the world of particles. He showed that behind classical trajectories, there might be a deeper wave picture. And this idea opened a new door that would explain atoms, chemistry, and a large part of modern physics. What really is uncertainty in Heisenberg's principle? The Heisenberg uncertainty principle is one of the most famous ideas in quantum physics, spreading far beyond laboratories and into popular culture. It is usually explained like this: you cannot know exactly where a particle is and how fast it is moving at the same time. At first glance, this may seem like a problem related to measurement, as if when we look at the particle, we disturb it. While measuring its position, we change its speed, or while trying to measure its speed, we disturb its location. This explanation feels partly intuitive, but the real depth of the issue is not there. The source of the uncertainty principle is not the weakness of our measuring devices, but the most fundamental structure of nature. Because in the quantum world, everything carries both particle-like and wave-like properties at the same time. An electron sometimes behaves like a tiny object caught at a single point, but the same electron, in some experiments, behaves like a wave spread through space. This is exactly where uncertainty comes from, this dual nature. When we think of a particle, we imagine it as a small thing located in a definite place. If it behaved completely like a particle, we could state its position very clearly. We would say, it is here, nowhere else. The probability would be concentrated at a single point. But a wave is not like that. A wave spreads through space, like rings on the surface of a pond. It is not squeezed into a single point. When we look at a wave, we can measure its wavelength, the distance between two peaks. In quantum physics, this wavelength is related to the particle's momentum. Momentum is roughly mass multiplied by velocity. So the wave gives us information about momentum, but it does not give us the same certainty about position, because the wave is spread over many places. This is where the basic tension appears. If you want to locate something very precisely, you have to squeeze it into a small region. But a single wave is not enough to do this. You need to overlap many waves with different wavelengths. These waves reinforce one another in some places, cancel one another out in others, and eventually form a wave packet concentrated in a small region. This wave packet now looks a little more like a particle, because the probability of finding it within a specific region is high. But there is a price for this. Since we used many different wavelengths to form the wave packet, the momentum no longer has a single value. There is now a possibility that the particle has different momenta, so making the position clearer makes the momentum more uncertain. You can also do the opposite. If you want to know the momentum very precisely, you need to define the wavelength very clearly. For that, you need a more regular, more extended wave. But as the wave spreads out, it becomes harder to say where the particle is. The uncertainty in position increases. That is why uncertainty is not an experimental error. It is not a flaw that can be eliminated with a more precise instrument. It is the necessary result of a quantum object, behaving both like a wave and like a particle. The Heisenberg uncertainty principle tells us this: nature does not carry some properties with unlimited precision at the same time. Position and momentum are not two independent pieces of exact information in the way we imagine in the classical world. As one becomes sharper, the other inevitably becomes blurred. In everyday life, we do not notice this, because the wavelengths of large objects are unimaginably small. The wave nature of a ball, a car, or a human being is practically invisible. That is why, in the classical world, objects appear to us as if they move in definite places with definite speeds. But when we go down to atoms and electrons, this comfortable picture breaks down. There, objects do not behave only like tiny marbles. They are also wave packets. That is why their reality does not fit our familiar logic of exactly here and moving at exactly this speed. This is the real meaning of the uncertainty principle. At the smallest scales of the universe, certainty is not as fundamental as we think. Some limits are not merely limits of our knowledge, they are limits set by nature itself. The uncertainty between position and momentum is not a simple disturbance caused by measurement, but a rule woven into the fabric of reality. How do electron got spin even though it doesn't spin? There are many things in quantum physics that seem to defy common sense, but spin occupies a place of its own. An electron does not rotate like a tiny ball, yet nature calculates it as if it were spinning. And this small strangeness is one of the keys to understanding why matter exists at all. There is a classic demonstration in physics classes. A professor sits on a rotating chair and holds a spinning bicycle wheel. Then he flips the wheel over and suddenly begins to rotate in the chair. This is a simple demonstration of the conservation of angular momentum. If the angular momentum of the wheel changes in one direction, the professor's angular momentum must increase in the opposite direction so that the total angular momentum remains the same. Now imagine an experiment that is very similar to this, but much stranger. An iron cylinder is suspended from a thin thread, and a vertical magnetic field is switched on. The cylinder immediately begins to rotate at a constant speed. At first glance, this seems to violate the law of conservation of angular momentum, because at the beginning, nothing appears to be spinning. But actually, something is. Or at least, in a certain sense, something is. The external magnetic field magnetizes the iron. This causes the spins of the electrons in the outer shells of the iron atoms to align. These electrons behave as if they were tiny bicycle wheels. The change in their angular momentum is compensated by the rotation of the cylinder. This explanation seems to make sense if we imagine electrons as spinning bicycle wheels. It may even sound reasonable, because electrons have a property we call spin, but there is a major problem here. Electrons absolutely do not spin like bicycle wheels. And yet, somehow, they seem to possess a very strange kind of angular momentum that exists without classical rotation. In fact, the spin of the electron is something much more fundamental than simple rotation. Like mass or electric charge, it is a quantum property of the particle. But this property does not merely cause magnets to behave in strange ways. Quantum spin turns out to be the visible expression of a much deeper property of particles, and this property is responsible for the structure of all matter. The experiment with the iron cylinder is known as the Einstein-de Haas effect. It was first performed by Einstein and de Haas in 1915. But this was not the first clue that electrons had spin-like properties. Earlier, while physicists were examining the specific wavelengths of photons emitted when electrons in atoms moved between energy levels, something strange had been noticed. Pieter Zeeman found that when atoms were placed in an external magnetic field, their energy levels split apart. This Zeeman effect could initially be explained by Lorentz, using ideas from classical physics. If you imagine the electron as a charged ball moving in a circular path around the atom, this motion produces a small magnetic moment. In other words, the electron creates a dipole magnetic field that behaves like a tiny bar magnet. Different alignments of this orbital magnetic field with the external magnetic field can split a single energy level into three. This seems reasonable. But then the anomalous Zeeman effect appeared. In some cases, the magnetic field split the energy levels even further. At the time, the reason for this was a complete mystery. One explanation was this: perhaps every electron has its own magnetic moment. In other words, perhaps the electron alone also behaves like a tiny bar magnet. Then both the orbital magnetic moment and the electron's intrinsic magnetic moment would contribute to new energy levels. But for this to work, one would have to imagine electrons as truly spinning charged balls. And this is where the major problem begins. To produce the observed magnetic moment, the surface of the electron would have to rotate faster than the speed of light. Wolfgang Pauli showed this clearly. And this was true even if one assumed that the electron had a measurable size. As far as we know, the electron is point-like. In other words, It has no surface in the classical sense. In that case, the classical idea of angular momentum becomes even more meaningless. That is why Pauli refused to interpret the electron's spin as classical rotation. Instead, he called it a classically non-describable two-valuedness. This phrase may sound cold and technical, but it actually says something very important. The electron may not be spinning, but it still has an intrinsic quantum property that can be measured in two special ways. One of the most famous experiments showing this is the Stern-Gerlach experiment. It was proposed by Otto Stern in 1921 and carried out by Walther Gerlach a year later. In this experiment, silver atoms are passed through a magnetic field whose strength changes from top to bottom. A silver atom has a single electron in its outer shell, and this electron gives the atom a magnetic moment. The external magnetic field deflects the atoms depending on the orientation of these tiny magnetic moments. If these were classical tiny bar magnets, we should see a blurred distribution on the screen, because the magnetic moments of the atoms would point in random directions. Some would deflect maximally upward, some maximally downward, and most would fall somewhere in between. But that is not what is observed. The atoms hit the screen at only 2 points. Only 2 points. The two extreme deflections. This shows that the direction of the electron spin is quantized. That is, spin does not take any intermediate value. When you measure it, it gives only one of certain possible results. Even stranger, if you change the direction of measurement, you again get two results. Measure vertically, and there are two results. Measure horizontally, and there are two results. It is as if this intrinsic property of the electron gives a two-valued answer, depending on the direction in which you question it. But this two-valuedness goes even deeper. To understand it, we need to look at how spin is written in quantum mechanics. In the mid-1920s, physicists had a new tool, the Schrödinger equation. This equation described quantum objects as wave functions, that is, as probability distributions. It was incredibly successful at explaining certain aspects of the subatomic world. But Schrödinger's first equation did not include spin. Pauli tried to fix this by making the wave function two-component. In this way, the wave function turned into a very strange mathematical object, a spinor. Soon afterward, Dirac developed a more complete equation that made the Schrödinger equation compatible with special relativity. Dirac was not actually trying to force spin into the equation, but the equation could only be written using spinors. Spin seemed to emerge naturally when relativity and quantum mechanics were combined. Spinors are very strange objects. If you rotate a normal object by 360 degrees, you return it to its original state. This is true for an arrow, a cube, a chair, or a planet. But for a spinor, 360 degrees is not enough. It needs 720 degrees, or 2 full rotations, to return to its initial state. This sounds impossible, but imagine rotating a cup without letting go of it. After one full turn, your arm becomes twisted. After the second turn, it untwists again. Spinors carry a similar kind of mathematical strangeness. That is why it is misleading to think of the electron's spin as a tiny ball rotating around itself. Spin is more like an intrinsic property related to orientation, symmetry, and the structure of the quantum state. The electron does not have a definite classical orientation, but it does have a definite angular momentum. Its orientation is uncertain, yet its spin angular momentum is precisely defined. However, we explain spin, we have a very powerful description of how it works. The electron is a spin one-half particle. So are the proton and the neutron. Particles with this kind of half-integer spin are called fermions. Particles with integer spin are bosons. Force-carrying particles such as photons and gluons are examples of these. This difference is not merely a technical distinction. Fermions and bosons behave in completely different ways in the universe. Bosons can pile up in the same quantum state. But fermions cannot share the same quantum state. This is the Pauli exclusion principle. And without this principle, there would be no periodic table. Electrons would not occupy different energy levels in atoms. chemistry would not work the way it does today. Matter would not form stable structures. In fact, this is partly why you do not fall through the floor right now. One of the things that makes matter matter is that electrons cannot be squeezed into the same quantum state. Electrons do not spin, but they do something far more interesting. What we call spin is not merely a strange property of a tiny particle. It is a doorway into the structure of matter. Perhaps it is a trace left in the deep fabric of reality, beneath space-time, by these strange mathematical entities we call spinors. Does observation collapse reality or create infinite worlds? Quantum mechanics is one of the most successful theories in the history of physics. It explains the structure of atoms. It explains chemistry. It makes lasers, semiconductors, computer chips, magnetic resonance imaging, and a large part of modern technology possible. Equations like the Schrödinger equation predict the behavior of the microscopic world with astonishing accuracy. But there is a strange problem here. The equations work. The predictions are correct. Experiments confirm the results. But when you ask this question, things become complicated. What is actually happening? This is exactly where the interpretations of quantum mechanics begin. Because physicists know how to use the equations, they can calculate where an electron is most likely to be found. They can say at what energy an atom will emit light. They can write mathematically which possibilities a particle exists in before measurement. But they do not agree on what this mathematics actually means in reality. Does a quantum particle really exist in many states at the same time before it is measured? When we make a measurement, is one of these possibilities really selected while the others disappear? Or do the other possibilities continue to happen in other worlds? These questions take us to one of the most famous debates in quantum mechanics, the Copenhagen interpretation and the many worlds interpretation. The basic difficulty of quantum mechanics is this. According to the equations, the properties of a particle are not definite in the classical sense before measurement. The position, momentum, or spin of an electron is not merely information that we do not know. According to quantum theory, before measurement, these properties do not have to possess a definite value. The particle exists as a combination of many possibilities. An electron may be here, and it may be there. Its spin may be up, and it may be down. An atom may exist at one energy level, and it may also exist at another. From the perspective of the classical world, this looks insane, because we never experience anything like this in daily life. A tennis ball is either here or there. A cat is either alive or dead. A glass does not stand both on top of the table and underneath it at the same time. But in the quantum world, the mathematics tells us this. Before measurement, a system behaves like a combination of possible states. To understand this idea, let us look at Schrödinger's famous cat thought experiment. Imagine there is a cat inside a box. Inside the box, there is also a radioactive atom, a radiation detector, a hammer, and a small vial containing poisonous gas. If the atom decays, the detector senses it. The hammer breaks the vial, and the cat dies. If the atom does not decay, the cat remains alive. According to quantum mechanics, radioactive decay is fundamentally probabilistic. The atom may decay within a certain period of time, or it may not. If we think of the atom's state quantum mechanically, before the box is opened, the atom is in a superposition of decayed and undecayed states. But the atom's state is connected to the cat. If the atom decays, the cat dies. If it does not decay, the cat lives. So what state is the cat in before we open the box? According to the Copenhagen interpretation, until a measurement is made, the system is in superposition. The cat is represented by a combination of the possibilities of being alive and being dead. But the moment we open the box and look, we see only one result. Either the cat is alive, or it is dead. The other possibility disappears. This is called the collapse of the wave function. So in the Copenhagen interpretation, measurement plays a very special role. Before measurement, the wave function carries many possibilities. After measurement, only one result remains. The world of possibilities turns into one single reality. This interpretation describes what we see in experiments quite well, because we really do not see a cat that is both alive and dead at the same time. we see one result. But the problem lies exactly here. Why does the wave function collapse? What exactly is measurement? Is it measurement when an electron hits a detector? Does a human being have to see the result? Is it enough for a device to record it? Where is the boundary between the quantum system and the classical world? The Copenhagen interpretation does not provide a very satisfying mechanism for these questions. It more or less says this: in experiments, we see one result. Therefore, we accept that the wave function collapses into one result during measurement. The mathematics works. The results come out correctly. You do not have to ask for more. The famous attitude often attributed to Richard Feynman is somewhat like this: shut up and calculate. But this does not satisfy everyone, because some physicists do not want only to calculate, they also want to understand what is happening in reality. This is where the many worlds interpretation enters the picture. The many worlds interpretation was proposed by Hugh Everett in 1957. According to this interpretation, the wave function never collapses. There is no such thing as collapse. The Schrödinger equation is always valid. When we measure a quantum system, one possibility does not disappear while the other remains. Instead, all possibilities happen, but in different branches. Let us return to the cat example. In the Copenhagen interpretation, when you open the box, the wave function collapses, and you see either the living cat or the dead cat. In the many worlds interpretation, when you open the box, it is as if the universe branches into two. In one branch, you see the cat alive. In another branch, another version of you sees the cat dead. Both outcomes happen. But you experience only the result in your own branch. At first glance, this idea seems incredibly strange, because you have to accept the existence of other worlds, perhaps even infinitely many worlds. In every quantum event, reality branches. One result happens here, while the other result happens in another branch. According to supporters of many worlds, this interpretation is actually simpler, because it does not add an extra rule such as wave function collapse. It simply takes the Schrödinger equation seriously and says that it is universally valid. If the equation preserves superposition, then superposition does not disappear. We simply find ourselves in one branch of it. But there is also a major problem here. If the other worlds really exist, why do we never see them? Why can we not communicate with other versions of ourselves? Why do we never experience the cat as both alive and dead at the same time? At this point, the idea of decoherence becomes important. Decoherence is the process that explains how superposition visibly disappears when quantum systems interact with their environment. A quantum system is never completely alone. The cat is not connected only to the atom. It also interacts with the air molecules inside the box, with photons, with heat, and with surrounding particles. You also interact with your environment. The detector also interacts with its environment. As these interactions increase, the different possibility branches of the system separate from one another. These branches can no longer interfere with each other. The environmental state associated with the living cat becomes different. The environmental state associated with the dead cat becomes different. These two states behave, in practice, like two realities that have separated from one another. In the Copenhagen interpretation, this process looks like the collapse of the wave function. In the many worlds interpretation, it is interpreted as the branching of worlds. The two interpretations can use the same mathematics, but they say very different things about reality. Copenhagen says that only one result becomes real during measurement, and that the other possibilities disappear. Many worlds argues that no possibility disappears, and that all of them occur in different branches. So which one is correct? This is where the difficulty lies. Even today, there is no definite answer. Different interpretations of quantum mechanics often produce the same experimental results. That is why it is very difficult to distinguish between them. The Copenhagen interpretation is more traditional and practical. Many worlds looks mathematically cleaner, but it demands a very large metaphysical price, because you must accept that other worlds are real. If the idea of randomness and superposition makes you uncomfortable, there are other interpretations as well. Interpretations such as the de Broglie-Bohm theory argue that there may be a more deterministic structure beneath the quantum world. Penrose's objective collapse ideas search for a deeper connection between gravity and quantum mechanics. So the debate is not only between Copenhagen and many worlds. What quantum mechanics means is still an open question. But the basic mystery around which all these interpretations revolve is the same. Quantum equations give us possibilities. Experiments show us one result. So, how do we pass from a world of possibilities to one lived reality? Maybe the wave function really collapses. Maybe all possibilities happen in other worlds. Maybe there is a deeper theory that we do not yet know. But one thing is certain. Quantum mechanics is not only a theory of tiny particles, it places the question of what reality is directly in front of us. And perhaps that is why, even after a century, physicists are still circling the same question. The equations work, but what is the universe actually doing? Why is the EPR paradox still one of quantum physics' deepest mysteries? Two great figures of modern physics defended almost opposite views about reality. According to Niels Bohr, in the quantum world, the state of a particle before measurement is not only unknown, but also unknowable. The particle should not be thought of as already having a definite value. Until measurement is made, it remains within possibilities. Einstein deeply opposed this. For him, reality could not depend on whether we measured it. The moon had to be there even when we were not looking at it. Even at the most fundamental level of nature, there had to be an objective reality, independent of measurement. Probabilities could only describe our ignorance, not reality itself. Bohr and Einstein debated this issue for years. One side argued that, as quantum mechanics suggested, uncertainty and measurement lie at the foundation of nature. The other side believed that this uncertainty was only the result of an incomplete theory. Perhaps the states of particles were already determined from the beginning, but we simply did not know them. The strangeness at the heart of quantum mechanics can be imagined with a simple dice example. Before an ordinary die lands on the table, it is in the air. But in a classical sense, which face will appear is already determined. In a quantum system, however, the situation is much stranger. A photon, electron, or atom does not have only one value before measurement. It is as if the die is 1, 2, 3, 4, 5, and 6 at the same time. The value appears only when measurement is made. The double-slit experiment also shows this. It is not enough to think of a single photon only as a tiny particle. The photon behaves more like a cloud of probability. It can pass through two slits at once, interfere with itself, and appear at a definite point only when it hits the screen. This was exactly what disturbed Einstein. Part of nature seemed not merely unknown before measurement, but genuinely indefinite. Together with Boris Podolsky and Nathan Rosen, Einstein developed the famous EPR argument against this idea. Their goal was to show that the Copenhagen interpretation was incomplete. At the center of the argument was quantum entanglement. Suppose a system with total spin 0 emits two photons at the same time. Since angular momentum must be conserved, if one of the photons is measured as spin up, the other must be spin down. These two photons are not independent. The moment you learn the state of one, you also learn the state of the other. Now let us send these two photons very far away from each other. Let the distance between them be so large that even light would need 1 second to travel across it. According to quantum mechanics, before measurement, both photons are in a superposition of spin-up and spin-down states. But they do not actually have two separate wave functions. There is a single wave function governing both of them together. When we measure the spin of one photon and find, for example, spin up, it becomes certain that the other photon will be spin down. It is as if the measurement on the first photon instantly affected the distant other photon. For Einstein, this was the problem. Because according to special relativity, no information can travel faster than light. So how could this be possible? According to EPR, the most reasonable explanation was this. The particles already knew what they were going to be from the beginning. Their states had been determined at the moment they were created. By making a measurement, we were only revealing information that already existed. This idea is called local hidden variables. We can think of it like a pair of gloves. When you find the left glove in one box, you instantly know that the glove in the other box is the right glove. But this does not mean that there is faster-than-light communication between the boxes. The information was inside the gloves from the beginning. Einstein wanted something similar for the quantum world. For about 30 years, this idea could not be disproved. Then, in 1964, John Bell entered the story. Bell found a way to test whether Einstein's idea of local hidden variables was correct. He expressed this through an inequality that looks simple but has very deep consequences: Bell's inequality. Bell's basic idea was this: if the properties of particles are determined from the beginning, then there must be certain statistical limits between measurements made in different directions. In other words, if the universe really works through hidden variables, the measurement results should never violate a certain mathematical inequality. But quantum mechanics said something else. When entangled particles were measured at different angles, the results should go beyond the limits allowed by hidden variables. This was a critical difference. Because the issue was no longer only a philosophical debate, there was now a distinction that could be tested experimentally. And when the experiments were performed, the result favored quantum mechanics. Bell's inequality was violated. In other words, particles did not behave as if they were carrying local information determined from the beginning. The kind of simple, classical, local reality Einstein wanted did not work. Does this show that particles really communicate faster than light? Most physicists approach this carefully, because we cannot use this effect to send information. The results of entangled particles are correlated, but this correlation does not carry a controllable message. Special relativity does not seem to be directly violated. Even so, the result is unsettling. Quantum mechanics seems to tell us this: reality may not be as local, definite, and measurement independent as Einstein wanted. Entangled particles, even when far apart, can behave as parts of a single quantum system. That is why the EPR paradox and Bell's inequality are not merely technical topics. They touch the most fundamental question about nature. Are the properties of the universe truly definite before we measure them, or does measurement play a fundamental role in bringing reality into being? What we know today is this: quantum mechanics explains experiments with astonishing accuracy, but the mechanism behind entanglement, superposition, and wave function collapse is still not fully understood. Perhaps the next great revolution in our attempt to understand what reality is will be born precisely from this question. Can quantum tunneling let you walk through a wall? The fastest baseball pitch ever recorded reached a speed of more than 170 kilometers per hour. That is truly impressive. But even a pitch like that cannot pass through a solid brick wall. In the everyday world, this is impossible. Unless, of course, the rules of the game belong to the quantum world. For a baseball to reach the other side of a wall, it basically has two options. Either it goes around the wall, or it breaks through the wall with enough energy. A ball can pierce a thin sheet of paper, but when it hits a brick wall, no matter how fast it is, it will most likely bounce back. Quantum particles, however, do not always behave this way. Sometimes a particle is found on the other side of a barrier that it does not seem to have enough energy to cross. According to classical logic, it should not be there. It should hit the barrier and bounce back. But when we measure it, the particle is on the other side of the barrier, as if nothing had happened. This phenomenon is called quantum tunneling. The reason this is possible is that particles do not behave only like tiny solid objects. They can also behave like waves. In quantum mechanics, we cannot state a particle's position with complete certainty. This is one of the things described by the Heisenberg uncertainty principle. When we have information about a particle's energy or momentum, we cannot have absolute certainty about its position. Within this uncertainty, there is a very small possibility. At the moment when we think the particle is here, it may be found on the other side of the barrier. It does not have to drill through the wall in the classical sense. Within the possibilities allowed by the quantum world, it can appear as if it had been on the other side all along. This may sound like a rare and insignificant strangeness, but in reality, without quantum tunneling, our existence might not even be possible. The sun is one of the greatest examples. The sun shines because of nuclear fusion. Hydrogen nuclei combine to become helium, and energy is released in the process. But for this fusion to happen, two protons must come very close to each other. The problem is that protons are positively charged, and they repel each other, just like magnets with the same poles facing each other. According to classical calculations, even in the hot and dense core of a star, overcoming this repulsion seems extremely difficult. The protons should not be able to get close enough to one another. And yet the sun still shines, because in very rare cases, protons cross this barrier through quantum tunneling. At that point, the strong nuclear force takes over and allows the protons to bind together. So the light of the sun is, in a sense, one of the small but continuous victories of quantum tunneling. This effect is not seen only inside stars. It also exists inside our everyday technology. Quantum tunneling plays an important role in the operation of flash memory. It can also create problems when microchips become extremely small, because electrons can tunnel out of the regions where we want them to stay and move somewhere else. As chips shrink, this evasive behavior of the quantum world becomes more visible. One of the most impressive uses of quantum tunneling is the scanning tunneling microscope. This microscope allows us to image individual atoms. A metal tip is brought extremely close to the surface being examined, but it does not touch it. According to classical physics, electrons should not be able to cross this gap. But thanks to quantum tunneling, some electrons pass through the gap and create a tiny current. Even the smallest bumps on the surface change this current. In this way, the microscope can map the shape of the surface at the atomic scale. With this method, it becomes possible to map DNA strands or build new structures atom by atom. Even stranger, quantum tunneling may be connected to the fate of empty space itself. What we call empty space is not completely calm. It is filled with quantum vacuum fluctuations. According to some theories, these fluctuations could, through a very special tunneling process, cause empty space to transition into another state. If this happened, small regions could form where the laws of physics might be different. These regions could expand at nearly the speed of light and change the structure of space. Ideas such as vacuum decay are connected to this. It sounds dramatic, but the universe has existed for about 14 billion years, and nothing like this has happened. So there is no strong reason to expect it to happen anytime soon. Quantum tunneling is one of the strangest and most useful features of quantum physics. It allows particles to appear beyond barriers they classically should not be able to cross. It plays a role in the shining of the sun, in modern electronics, in microscopes that can see atoms, and perhaps even in the deepest fate of the universe. But unfortunately, it is not enough to make a baseball pass through a wall. Is consciousness born from quantum collapses in the brain? Nobel Prize winner Roger Penrose is regarded as one of the most brilliant living physicists, with work ranging from black holes to cosmology. And then he has this idea. Consciousness may arise from quantum processes taking place inside the brain. For a long time, most scientists saw this as a charming oddity. After all, someone like Roger Penrose could probably have at least one crazy theory without being expelled from the club of super-intelligent people. The most common objection to this idea was also quite simple. Quantum effects cannot survive long enough in a warm, wet, chaotic environment like the brain. Quantum states are fragile. When they come into contact with the environment, they break down very quickly, and the brain is exactly inside this storm of contact. But new studies are making this old objection a little harder to maintain. Because evidence is emerging that microtubules, one of the most important candidate structures for Penrose's quantum consciousness idea, may really possess large-scale quantum behaviors. So was Penrose right from the beginning? Could our consciousness be the surface of a much deeper quantum event than we imagine? The story begins when Penrose, as a young man, attended a lecture on Gödel's incompleteness theorems. Kurt Gödel's theorems show the limits of mathematics itself. Put simply, if there is a consistent mathematical system capable of expressing basic arithmetic, then within that system, there are statements that are true, but cannot be proven by the system's own rules. This is a very strange idea, because we usually think of mathematics as the language of certainty. But Gödel tells us this: if the system is consistent, it is incomplete. If it can prove everything, it risks being inconsistent. In other words, inside mathematics, there is a gap that cannot be completely closed using mathematics' own tools. Penrose takes an interesting step here. According to him, human beings can sometimes see a truth beyond formal proof. Mathematicians can be strongly convinced that certain propositions are true, even when there is not yet a formal proof. From this, Penrose moves toward the conclusion that the human mind may not work only like a classical algorithm. Conscious understanding is not just computation. If that is true, then explaining consciousness as an ordinary computer process may be incomplete. This idea later became known as the Penrose-Lucas argument. Of course, there are many objections to it. Thinking that we know something does not mean we truly know it. Also, even if we accept that the human mind can surpass Gödelian limits, connecting this directly to consciousness is a major leap. But Penrose does not stop there. If consciousness is not classical computation, then what kind of physical process could it be? Now we come to the strange part. According to Penrose, the answer may be hidden in quantum mechanics. Quantum mechanics describes the world of very small scales. Electrons, atoms, molecules, and other quantum objects behave in ways we are not used to in the classical world. A particle can exist in more than one state at the same time. We call this superposition. Two particles can have mysteriously connected properties even when they are far apart. We call this entanglement. And when a quantum system is measured, these blurry possibilities collapse into a single result. We still do not know exactly how this collapse happens. This is called the measurement problem. Even about a century after the discovery of quantum mechanics, what we really mean by measurement remains both a philosophical and physical mystery. What interests Penrose is this: wave function collapse seems to contain a genuinely random element. If the result is truly random, then no classical algorithm can calculate it perfectly in advance. According to Penrose, conscious reasoning may be connected exactly here, to a quantum process that goes beyond the limits of classical computation. But there was a major problem. Quantum behaviors are usually observed under extremely delicate conditions. Particles must be isolated from the outside world. The system must be cold. Environmental noise must be minimized. This is why building a quantum computer is so difficult. The brain is the exact opposite. It is warm. It is a wet biological environment. It is filled with constant chemical and electrical interactions. Expecting long-lasting quantum coherence in such a place seemed almost impossible to most scientists. This is where Stuart Hameroff enters the picture. Hameroff is an anesthesiologist, and he has long been interested in consciousness. The structure that caught his attention was the microtubule, found inside cells. Microtubules are tiny tubes that form part of the cytoskeleton. They help maintain the shape of the cell, play a role in transporting proteins, and help separate chromosomes during cell division. But for Hameroff, what made microtubules especially interesting was their highly ordered, almost crystal-like structure. They are made of molecules called tubulin, and the orientations of these molecules may form an order capable of carrying information. Hameroff thought that microtubules might not be merely mechanical support structures inside the cell. Perhaps they worked like molecular computers. Perhaps they stored information, processed it, and formed a deeper layer of computation inside neurons. Later, Hameroff encountered Penrose's ideas. Together, they developed a much more ambitious theory: orchestrated objective reduction. According to this theory, quantum states form inside microtubules. These states enter superposition, and then they collapse at a certain threshold. And according to Penrose, these moments of collapse may be the basic building blocks of consciousness. In other words, consciousness may be the sum of small quantum collapse moments continuously taking place inside the brain. This theory has existed for more than 30 years, and to be honest, it has not been taken very seriously by much of the scientific world. Because the biggest problem remained the same: how could quantum coherence be preserved in a warm and messy environment like the brain? But in recent years, interesting findings about microtubules have begun to appear. In 2013, evidence was found suggesting that microtubules may display large-scale quantum resonance. This suggested that they might possess long-range electrical conduction properties and perhaps play a role in information processing or memory-like functions inside the cell. More recently, Nathan Babcock, Philip Kurian, and their colleagues published a study on ultraviolet superradiance in tryptophan networks in biological structures. These tryptophan networks are found in the tubulin molecules inside microtubules. Superradiance is different from normal fluorescence. In fluorescence, molecules absorb light and then release the energy slowly and individually. But in superradiance, many molecules behave not one by one, but like a collective quantum system. Excited states resolve together, producing a burst of light that is much brighter and much shorter than ordinary fluorescence. This is a very quantum effect, because the parts of the system do not behave separately, they behave together, like an entangled whole. The researchers argue that they saw signs of such superradiance in tryptophan molecules inside microtubules. The amount of emitted light was hundreds of times greater than what ordinary fluorescence would predict. According to their model, this result could only be explained by a collective and quantum-like process. Simulations also showed that these excited states could spread across microtubules over much longer distances than expected. This does not mean that consciousness is quantum. It is far too early to say that. The new study does not directly prove consciousness. It does not confirm Penrose and Hameroff's theory either. But it may show something very important. Some biological structures in the brain may display stronger quantum behaviors than we thought. And if microtubules really form an additional layer of information processing inside neurons, then the brain may not be made only of synapses and electrical firing. Inside neurons, there may be another world of computation operating at a smaller scale. This also leads to an interesting implication even for artificial intelligence. If we think we can simulate human intelligence simply by copying the number of synapses, perhaps we are missing a major piece. Because if each neuron contains billions of microtubules, and if these work through fast, complex, perhaps quantum-like processes, then copying the brain may be far more difficult than we imagine. In the end, we do not have a definite answer. Was Penrose right? We do not know yet. Do microtubules produce consciousness? We cannot say that. Is there real quantum information processing in the brain? That too remains an open question. But the old objection no longer looks as comfortable as it once did. Saying, the brain is too warm, so quantum effects cannot live here, may have been a judgment made too quickly. Perhaps biology has found ways of protecting quantum sensitivity that we do not yet fully understand. And perhaps consciousness is not an ordinary electric lamp burning inside the brain, but the surface glow of a much stranger quantum order, vibrating, connecting, collapsing, and rebuilding itself at microscopic scales. Could quantum tunneling be happening inside your DNA? Quantum biology is still a somewhat speculative but extremely exciting field of science. The question it asks is actually very simple. Could quantum mechanics, the theory that explains the strange rules of atoms, molecules, and the subatomic world, also play a special role inside living cells? In other words, are there processes in living organisms that can be understood not only through classical chemistry, but with the help of quantum mechanics? This idea is not entirely new. The idea of quantum biology has been around since the 1930s, but for a long time it was seen mostly as speculation. In recent years, however, experiments in biochemistry laboratories, especially those using sensitive methods such as spectroscopy, have begun to suggest that some biological mechanisms may not be fully explainable without quantum mechanics. That is why quantum biology is not the subject of a single field. Quantum physicists, biochemists, molecular biologists, and chemists all gather around the same question. Because life, at its deepest level, is made of molecules. Molecules are made of atoms, and the rules that determine how atoms behave are the rules of quantum mechanics. In one sense, this is not surprising. Of course, life ultimately depends on quantum mechanics. Non-living matter depends on it too. Stones, metals, water, air, proteins, DNA, all of them are made of atoms. But this simple fact is not the real question quantum biology asks. The real question is this: do the strange, counterintuitive features of the quantum world actually play a functional role in living systems? Because quantum strangeness is extremely delicate. In laboratories, physicists cool systems almost to absolute zero, work in vacuum environments, and reduce external disturbances as much as possible in order to preserve quantum effects. A living cell, however, is warm, wet, complex, and noisy. Molecules constantly collide, vibrate, and move. At first glance, preserving quantum effects in such an environment seems almost impossible. But nature sometimes finds cleverer ways than our laboratories. One of the strongest examples of this is quantum tunneling. In the classical world, a particle must have enough energy to overcome a barrier. If you want to get a ball to the other side of a wall, you either throw it over the wall or give it enough energy to break through the wall. But, in the quantum world, particles can sometimes appear on the other side of a barrier, even if they do not have enough energy, as if they had not passed through the wall, but had suddenly appeared on the other side. This is not just a theoretical oddity. Quantum tunneling plays a role in the shining of the sun. In the sun's core, protons need to come close to one another. But because protons have the same electric charge, they repel each other. According to classical calculations, overcoming this repulsion should be very difficult. But thanks to quantum tunneling, some protons can cross this barrier and fusion can occur. There is evidence that the same mechanism also operates inside living cells. Enzymes are the chemical workers of life. They accelerate reactions inside the cell to an extraordinary degree. For a long time, exactly how enzymes do this remained a major question. Then it became clear that some enzymes may be able to move subatomic particles, such as electrons or protons, from one part of a molecule to another through quantum tunneling. This is fast, efficient, and very important for understanding certain stages of living chemistry. An even more interesting question concerns DNA. The two strands of DNA are held together by hydrogen bonds. Protons play an important role in these bonds. If these protons move into the wrong position, an error may occur when DNA is copied. This can lead to mutation. The big question here is this: do protons really shift position in a classical way? Or can they cross to the other side through quantum tunneling without overcoming the energy barrier? This is still an open question. It is not known with certainty how important quantum tunneling is in DNA mutations, but if it truly plays a role, its impact could be enormous. Because mutations are connected to some of the most fundamental processes of life, from evolution to cancer. Another impressive example is photosynthesis. Plants and some bacteria capture sunlight, convert this energy into chemical energy, and produce the fuel of life. In this process, the energy carried by light is absorbed by chlorophyll molecules and delivered to the reaction center. Classically, one might imagine the energy traveling along a single path. But some experiments suggest that this energy may be able to try multiple paths at the same time, instead of following only one. This is the idea called quantum coherence. It is like a quantum system carrying multiple possibilities at once. Instead of choosing a single route to reach the reaction center, the energy seems to explore many paths at the same time and find the most efficient one. If this is true, the extraordinary efficiency of photosynthesis may be related not only to chemical organization, but also to the multiple path logic of the quantum world. The final example is so beautiful that it almost seems poetic: bird navigation. The European robin migrates every year from Scandinavia to the Mediterranean. It is known to navigate by sensing Earth's magnetic field. But Earth's magnetic field is very weak. It is much weaker even than a refrigerator magnet. So how can a living organism detect such a weak field? One of the most interesting explanations involves quantum entanglement. In the bird's retina, there is a light-sensitive protein called cryptochrome. Inside this protein, two electrons may become quantum entangled. Entangled particles behave like a single system, even when there is distance between them. This delicate quantum relationship may be sensitive to the connection between the bird's direction of flight and Earth's magnetic field. This has not yet been fully confirmed, but if it is true, quantum mechanics may play a role in determining a bird's migration route. In other words, one of the strangest ideas of the quantum world may be working silently inside a living eye. Quantum biology is still a young field. Many questions remain open, and many claims still need careful experiments. But the idea is incredibly powerful. Perhaps life does not merely depend on quantum mechanics. Perhaps life has also learned to use some of the strange features of the quantum world. If this is true, then what we call life is not only a collection of chemical reactions. Even inside the warm and complex environment of the cell, nature may be using the strange tools of the quantum world. In the shining of the sun, in the speed of enzymes, in changes in DNA, in the efficiency of photosynthesis, and in the migration routes of birds, the same deep question may be hidden. What if life is far more quantum than we thought?